So continuing with Bessel functions of the first kind. The textbook says without elaboration that it's very helpful to have an integral representation of Bessel functions. I think we're going to put that comment out there. Anyway, I guess. Well, explaining that, although I can say that I actually have personally found integral representation of Bessel functions to be useful in my own research. So, because what we have now for Bessel function, the infinite series representation that was arrived at, I'm using a generating function, which is also obtained. It was also obtained some time ago using Fourier's method. So what we could do is use a theorem for complex analysis, known as a residue theorem, to obtain another representation of a Bessel function for the first time. So what is a residue theorem? That's what we have here. If we have a function f of z that can be written this way as a Lorentz series, so it looks like a power series, except we have both positive and negative powers of z minus the center. So we're going minus infinity to infinity instead of the customary 0 to infinity for a power series. So if you have a function represented that way, then you take the integral of f of z over a positively oriented simple closed curve in the complex plane, any such curve. For example, a circle, which is what we'll use later. It turns out that the value of its integral is 2 pi I times the coefficient of the Lorentz series corresponding to n equal minus 1. There are a lot of freaky theorems for complex analysis. I remember my complex analysis professor always state some theorem and he'd say, oh, there's nothing like this for reals. Okay, yes, we heard it the first time.
There's nothing what?
There's nothing like this for real analysis. Yeah, so there's certain things that happen in complex land that are very different. All right. If we ever offer a class of complex analysis again, maybe you can find that out. Okay. So let's apply this theorem to a generating function for Bessel functions. That's what I've done here. So this exponential right here, that is a generating function that we used last time to obtain Jn of x. But I'm going to scale it by 1 over t to the n plus 1. Because this exponential by itself has this series. That m going to minus j to infinity. And that would include jm times t to the m. But if I divide by t to the n plus 1, then that gets accounted for in here. Okay. So then, there's something I'm going to take a look at here. Okay. Okay. I'll just make sure I have this correct. The notes. check something from last time's notes. Okay. I've forgotten that here we have this minus from j to infinity. So at least the notes from last time are correct. Now, okay, so that's what we have here. So jm to the m comes from generating function, then it's scaling by this. Now, by the residue theorem, the value of this integral will be 2 pi I times the coefficient of this series, this Laurent series, corresponding to t to the minus 1. But for this to be t to the minus 1, that would require that m equal n. Thus we get jn of x. So right here, also already we have this integral representation of jn of x. That's equal to this integral divided by 2 pi I. Now, keep in mind that to this point, the only other representation we've seen of jn of x is an infinite series. This can be much more practical for computational purposes, because all you have to do is evaluate this integral, which can be done generally a lot more cheaply than evaluating an infinite series. That would have to be truncated at some point, of course. So already we see one benefit to having an integral representation rather than a series. Now C is allowed to be any possibly oriented simple closed curve that has to contain, now for the residue theorem, it has to contain the center of your Laurent series expansion. In this case, the center is 0. So as long as C is a curve that contains the origin, then this result is valid. But we might as well pick a particularly convenient curve for C. Which we'll do. We'll just choose C to be the unit circle. What could be simpler than that? So we use polar coordinates. So t is supposed to be, the variable t is for corresponding to points on the curve C. Well, the unit circle in the complex plane consists of all points of this form, e to the I theta, where theta goes from 0 to 2 pi. So that's the substitution now we'll make. T is equal to e to the I theta. So then we have this for dt, taking the derivative. So now this integral becomes this when we make that, well, I guess normally called a u substitution, but it's a t substitution. But then this difference of exponentials right here, e to the I theta minus e to the minus I theta, that's the same as 2i sine theta. So the 2's will cancel. Let's see. All right. So then I'm left with e to the I x sine theta from a numerator. And then this e to the I theta will cancel with the e to the I times 1 theta down here. We're still going to have e to the I n theta in the denominator, but we just bring that upstairs. So once we simplify as much as we can, then this is the exponential that we get. I know a lot happened on this slide, so I can do the most important thing. the one key step that does all this. Any questions about how we got here? Now, so all this is equal to 2 pi I, Jn. We'll cancel the i's, and then we'll divide both sides by 2 pi. So now Jn is 1 over 2 pi times this integral. But it would be nice if we could have the integral of a real value function, not a complex one. So if I use this relation, that's likely familiar to you, EVI theta equals cosine theta plus I sine theta. So I apply that down here, where in this case theta is equal to this whole expression in parentheses. Now I have cosine of this strange argument plus I sine of this strange argument. It does seem weird to be taking a cosine of a sine. Now, we break this up into 2 integrals. So this comes from a real part, and it actually simplifies to this. Instead of integrating from 0 to 2 pi and dividing by 2 pi, you can also integrate from 0 to pi and divide by pi, it's equivalent. And it turns out the imaginary part, it comes from integral of this sine of x sine theta minus sine theta. So this turns out to be 0. Now, I don't expect you to see, just from what's written here, why it's valid to rewrite this integral as this one, and I also don't expect you to immediately see why this integral must be 0. So I'm going to take a little time to show you both. But first, make sure that everyone is okay, at least up to this point. Before I justify the rest. And use these trigonometries to help me. So cosine b, actually it's a minus b is what I need here. A cosine b minus sine a. Sine a minus b. So sine a cosine b. Oh, well, the cosine one is a plus. The sine one is a minus. Cosine A. Okay. And I also need these symmetries of cosine and sine, that cosine of minus A is the same as cosine of A, cosine of the unit function, whereas sine is odd function. Basically, a negative can be pulled out effectively. Now I'm going to use these on both of these functions, cosine and sine of this strange argument, x sine theta minus n theta. So what happens when we do that? I have cosine x sine theta minus n theta. That's going to give me cosine of x sine theta cosine n theta plus sine x sine theta. Okay, and similar for sine, all that. Minus cosine. Okay. Okay. So what I want to take a look at is, if we consider theta from, because in the integrals on the previous page, we have we're integrating theta, d theta from 0 to 2 pi. So I want to examine the cases of theta going from 0 to pi, and theta going from pi to 2 pi separately. Okay. Now, so if we use these formulas exactly as I've written them, for theta between 0 and pi, but what happens if we add pi to our arguments? So for instance, cosine of theta, or any variable a plus pi, what happens when you do that? Well, that's equal to cosine a cosine pi minus sine a sine pi. The sine of pi is 0, and cosine of pi is minus 1. So we get minus cosine of a. And similarly, if I consider sine of a plus pi, you can see my identity. So I have sine a cosine pi plus cosine a sine pi. Again, sine of pi is 0, cosine of pi is -1. So I get minus sine of a. Okay. So I throw a lot of trig at you. And now we can see what we get from all of it. So now let's see what happens. I hope I have room for this. Might not. I wasn't expecting this part to take this long, but okay. I'll just do this in more than one line. But yeah, I don't know if this is like throwing it. Oh yeah, this thing is 0. Thing might work for it. So what I'm going to do here is I'm going to replace theta throughout by theta plus pi. See what happens on the other half, or bottom half of the circle. So then I have to replace theta by theta plus pi throughout on the other side. I still run out of room. Oh.
That's what I did.
Okay.
It's because they were open.
Okay. Now, so what will happen is, in the case of cosine, this is as bad as it gets lengthwise, so I'm not going to start simplifying things. I want to see how this relates to the original, where it's just theta. That will tell me the symmetry of this function. Okay, now, so for instance, when I have sine of theta plus pi, here, that's going to be the same as minus sine theta, so I can take that into account throughout. Okay, so that's going to be minus x sine theta. Okay. And then we have flip over here, sine of minus x theta. Okay. Now here is cosine. Cosine of minus something is same as what happens if you go over minus, because cosine is the even function. So then that minus can get ignored. Okay. And then I have over here, though, this minus in the sign gets pulled out. Because of sine being an odd function. Now, here I have cosine of a plus pi, sine of a plus pi, but if I use sine of a plus n pi, okay, so that would be a little bit different. Okay. I have to work those out. Not just adding pi to the argument, but n pi. So in this case, like cosine of n pi is minus 1 raised to the n power. Whereas sine of n pi is 0. So you're going to get minus 1 to the n. And here too, I'll have minus 1. So then if I use this down here, actually I'm starting to not like which way this is going, but so then this is going to be the same as, I guess we're not planning this. So cosine of, that's going to say is minus 1 to the n, cosine n theta. And then I have this one is also going to be minus 1 to the n. Sine n theta. What I wanted to arrive at was that I wanted to recover just this. In other words, even symmetry, but it's actually yeah. I think I was supposed to do this a little bit different. Sorry about that. Ah, maybe what I was supposed to do was this. Instead of adding pi to the arguments, but there's one way to get from one half of the circle to the other. I could do this. Cosine of 2 pi minus a. That would be cosine of 2 pi cosine of a plus sine of 2 pi sine of a. But sine of 2 pi is 0, cosine of 2 pi is 1, so you just get cosine of a. And then sine of 2 pi minus a, so that's sine of 2 pi cosine of a, that part's going to be 0. And then I have minus cosine of 2 pi, which is 1, sine of a, so that's sine of a. Okay, yeah, I think that's what I needed to do. Okay, so that is where Okay. Let's try this again, shall we? Alright, we'll have to keep in mind still have stuff to cover after this. Okay. Okay. So now I have, but that's just going to be sine 2 over minus beta is just the same as sine of all x, so that part stays the same. Okay, then cosine 2n pi minus theta, that's going to work out the same also. All right, so that's just, okay, so that part stays the same too. Okay, good. Now this is working out how I wanted. Dang it. Okay, and as for the rest of it, this is plus. All right, so now we have some. I still have that. And that's unfortunate, but I think in the end that's not going to be a problem. Okay, so then if I do the same thing with sine, oh, that's actually going to be a plus. I may have to abort this just because of time. Okay. Oh, I know what I could have done differently. Because for this part right here, yeah, that's what I should have done. I shouldn't have broken up like this. I should have x cosine, right? And then here I have minus 2 pi n. And then this part only gets the cosine of n theta. Yes, because cosine being 2 pi periodic, that ends up not affecting anything. And I just get sine of that and cosine of that. Okay, so that part works out quite nicely. Okay, that's for the rest. So, right. Okay. And here plus, and this ends up being so then if I throw in a 2 plus plus 2 pi n. And then here I have sine of minus. Oh, no, I just still n theta. Then that should be a minus 2 pi n. And what would happen with the rest of this? Okay. was doing this in my head well before class, and it was working out then, and for some reason it's not working out now. It's driving me nuts. What's supposed to happen is I get a situation where the integral, basically I show that the integral of this from 0 to pi is the same as the integral of this from pi to 2 pi. Therefore, you end up with two of these, and then you have 2 over 2 pi, and you get 1 over pi. Similarly, the integral of this from 0 to pi should be the negative of the integral from pi to 2 pi, and therefore the integral as a whole should not be 0. That's what's supposed to happen due to the cosine being an even function and sine being an odd function. And I am mortified that I'm not using the right approach to actually reveal that. You know, trying to do two different kind of ways to map the one half of a circle to the other. But yeah. It was something that I'll probably be revisiting after class. So. So I don't want this to bring us off the edge. Okay. So yeah, because I'd even used these very identities to work that out. I will say though, if I take this and I threw out, if I replace theta by minus theta, then I swear to God, we'll move on after this. If I replace theta by minus theta, it's going to get cosine of now. On the one hand, the minus passes through the sign, it gives me this. But then cosine is an even function. That goes out of the way yet. And then I get cosine of plus n theta. But again, so I have that cosine here. Because it's plus n theta, the trig identity leads me to a minus in between the two terms. Then I have sine of minus theta, the minus passes through here. And then, but then the minus comes out again. And then sine of minus, but this becomes, okay, there's sine of n theta. So then, yeah, yeah. So it turns out what you get is the same as you had before. So it is not affected by the symmetry. by going from 0 to replacing theta with minus theta. Whereas if I do the same thing down here, and I replace theta by minus theta throughout again. Okay. Then I have sine of minus x sine theta, and this minus is going to pass out through here. Now, because I have x sine minus theta plus n theta, that becomes a plus. And then I have cosine of minus x sine theta, but cosine is an even function. So that's going to go away. Okay. Yeah, and then we're supposed to get here. Yes. And that is equal to the same thing except there's a minus. Okay, so that's what happened with cosine versus sine. Here, changing theta to minus theta did not affect. Here, changes to sine. So, because of the evenness of cosine versus the oddness of sine. Okay. So, and because of the periodicity, okay, there had to be more to it than this, but that's what this is resting on, basically. So, step in the right direction. And for now, we'll just have to be happy with that. If time permits, maybe I'll write it up later and put it in the notes. Sorry about that. I always say anything unscripted teaching can go wrong, and I violate that rule all the time. Because only in a minority of instances does it become a turn out disastrously exist.
Is a lot of trade.
What?
Is a lot of trade.
I'm sorry, I'm not understanding what you're saying.
It is a lot of trade.
Yeah. So. Okay. Now, the point is, Jn is now equal to this. Integral of a real value function. And if I said J and n, set n equals 0, so here I have J0. Just what that's supposed to do. Now, everything I showed you applies to special functions of integer order, but the residue theorem can be applied just as easily to special functions of non-integer order. So this relationship that we used previously for Jn still holds for whatever non-integer order nu that we have here. By the way, if anyone is anyone watching now or watching this later, goes ahead and works out what I was trying to do earlier, please do not tell me. I'll take care of it from a class. So I don't need a student scooping me right now. So, not when I've already experienced difficulty. Hope you understand. Okay. Go ahead and work on it if you feel like it. but then keep it to yourself, please. All right, now, so one key difference between Bessel functions of non-integer order versus integer order, so we just saw that the same integral representation is available no matter what, is that this relationship, when you negate the order, so in case where nu is an integer, that's the same as multiplying by -1 to that order. That doesn't hold when the order is not an integer. Because what happens when you are, if you're trying to solve Bessel's equation of a non-integer order using Frobenius' method, you actually get two linearly independent solutions. Whereas if you use Frobenius' method with integer order, you only get one linearly independent solution. The other one breaks down, and you define it a different way, like using like reductional order. So it's because these two solutions end up being linearly independent in the non-integer case, that's why we don't have this. So while there are some helpful similarities between integer and non-integer cases, there are some differences too to be aware of. Now these recurrence relations, which you will work out as one of your homework problems, those apply in integer and non-integer cases. But now, let's suppose we have some set of functions indexed by this order nu, not necessarily Bessel functions, but they do set, let's assume that they satisfy these recurrence relations. So what I'm going to do is substitute into Bessel's equation and see what we get using these recurrence relations. So for example, what I have here, I can divide by 2 and I have an expression for a first derivative of J nu. So then the second derivative would be first derivative of this divided by 2. So this relationship gives me this for second derivative. And I have that here also, same thing for first derivative. So then I'll work these out, or write these out, and what I've done here, these terms are multiplied by x squared. These are multiplied only by x, but I'm writing it as x squared over x for the purpose of grouping all of these things together into one. Okay. Also, here I have z nu. I'm using this recurrence relation to rewrite that. So I took this one, divided both sides by 2 nu, or divided by 2 nu over x, and made that substitution here on the right side. Looks like there's another recurrence relation here, but it might not include it. Oh, no. Alright, to get from this step down to this step, okay. I'm gonna put in an intermediate step, just to make that clear. Okay. So I'm going to simplify what we have out here. So I have nu squared over nu, so I'm just gonna have nu up front. And then here I have x over 2, here I have x squared over 2. So I'm going to make this x squared over 2x. So I can distribute a 1 over x through here. So now, okay, and then I'll move nu inside. So now we have x squared over 2 on the outside, everything else is inside. So now I can put these terms together with these. So, okay, so I can have minus all that, minus again. Oh, all in the square brackets. So if I'm messing with these, I get to incorporate them in here. So now notice here I have 1 over x, c nu minus 1, and minus nu over x, c nu minus 1. So I can combine this term and this term to get this term. And then similar over here, like this term and this term involving z nu plus 1. I combine to get this term. Now for the last stage, to get from here to here, the easiest way to see that if I take, for example, this recurrence relation and this one, suppose I add them together. Well, the new j nu plus 1 in the 2 will cancel out. I'll just have j nu minus 1, 2 of them. That's equal to this plus this. And then similarly, if I were to subtract these, I can get the j nu minus 1s to cancel. I'll have a difference of these. That's the trick we used to get from here to here. I should point out that something like this plays a role in the homework problem about these recurrence relations. So there's another breakdown. So now we have this. And so it turns out that any sequence of functions that satisfies these two recurrence relations also satisfies Bessel's equation. And vice versa. So we have an alternative characterization of solutions of Bessel's equation. Or at least it'd be a scalar multiple of like B Bessel functions. So it's kind of like we have an if and only thing going here. Now why this is of interest is, instead of z nu of x, suppose I have z nu of kx, where k is some scaling constant. So then I can carry out the same kind of manipulations. And what I end up with, so before I got minus x squared z nu. Well, now I'm going to get minus k squared x squared z nu. Where everything's evaluated at kx instead of x. So then that modified function is a solution of this ODE that's very similar to the Bessel equation. It's just that wherever you saw x in the original, well, you still have plain old x squared and x out here. But now you have kx, the whole thing squared here. The reason why this is of interest is, and actually something I mentioned last time too, for certain partial differential equations, PDEs, where you solve them by separation of variables, this modified form of Bessel's equation pops out. And at least you're able to express the solution of that in terms of the Bessel functions of the first kind. And I actually mentioned one example of this last time, and that is solving Laplace's equation on a disk. So one of the ODEs that you separate this PDE into ends up being exactly this. So your solution involves a Bessel function. You just have to select the right argument. It's kf or k, the value of k. So someone who's taking, for instance, Math 4 next semester might see that there, depending on what's covered. It was going to be a preview of this. I show you all Math 2 today. Okay. Which one that's the end of the notes? Yeah, that's the end of the notes. Okay. All right. And you're all let's go over any questions.
Yeah. Can we go over homework 8.2.8?
828.
Yeah.
Okay.
Yeah, I was just wondering how do we set up the scalar product like integral, because I was kind of confused about like the format of the equation at the top.
Okay. All right. So the idea is your scalar product will be this is a generic Sturm-Liouville equation. Okay, so you're working with generic interval AB. So the integral from A to B of u prime of x, u n of x, times p of x. So that's the scalar product to start with.
Can you say it again?
So the integral from A to B of u prime, u m prime times u n prime times p of x. And but the goal is to show that that is equal to 0. And so what you want to, because since um and un not differentiated are orthogonal with respect to the standard scalar product. So you have that the okay. Right. So one thing you can use is that I guess a scale product of um of x times un of x without the p of x that is 0, but that doesn't necessarily help you. What can help you is scalar product of times the operator applied to So in other words, times, okay, times this, just the first part. That's the Sturm Liouville operator. Because the idea is operator is equal to the minus lambda weighted function. Oh, the function of x. Okay, now hold on a second, I need to quickly unshare and reshare. I want to make certain that I'm not telling you something wrong. I thought that I had. But I worked this out previously, but it was a while ago. I'm not finding it. I always write up solutions for homework to use for grading purposes, but I just hadn't done this one yet. But I distinctly remember looking at this particular problem. I thought that I had written something down about it. And of course, because I need it in class now, am I finding it? No. We have
You answer the question.
Now it's confused.
yeah. Nine. This is actually not a self-adjoint case. Oh, no, not self-adjoint. It bugs me that this one-way function of w of x is sitting there. I don't like that. Because then does that mean that this p of x supposed to be piled on top of that? Or actually replacing it? So okay. I'm gonna also do this in writing, just so that you have things that you can work with. Then return to the notes. Okay. Wow, we're gonna almost the whole time.
I know.
Okay, so. Alright, so we'll show that the product of U and prime. I'll write this in the goal. First thing I'm going to make an assumption. Assume that the weight function given the original, this we're supposed to use assume minus 1. As I'm really not sure what it's doing yet. X 0 when m is not equal to n. Really, the eigenvalues are state. You can use this at the integral from infinity of mx times operator mx. There's no weight function present equal to 0. Distinct eigenvalues, where the operator in question is the operator from a problem. So it's the first portion of the eigenvalue problem statements. Okay. So you use this. So if you get from this to this, then you know 0. Okay. All right. Any other homework questions?
Speaking.
What now?
This weekend.
Oh, right. Okay. Or from the online audience. Oh. Less.
Yeah, so,
For what?
oh, she was asking which homework it was.
Yeah.
Oh, right. Okay. I gotta be done. Okay, I guess we're all done.
I don't know, you could talk like 3 minutes.
No.
To get the whole entire.